I'm going to prove that every triangle is isosceles, every triangle, the lopsided ones, the scrawny ones, the one you draw to specifically avoid being isosceles. All of them, secretly, have two equal sides. Obviously that's false. You can see it's false. Draw a triangle with three different side lengths, and there it is, a counterexample sitting right in front of you. So here's the deal. I'm going to walk through a real proof step by step, and I promise you every single move is going to look completely legitimate. Congruent triangles, angle bisectors, the stuff you'd see in any geometry class, and at the end it'll say the two sides are equal. Your job is to catch the lie, because there is exactly one, and it's not where you think. It's not some sneaky divide by zero thing. It's sneakier than that. I got fooled by this the first time, and honestly the second time too, because the broken step is the one that looks the most obvious. Keep your eye on that. The move you'd never bother to check is the one doing all the damage. Okay, let's build the trap. Here's our triangle. I'm calling the corners A up top, B down on the left, C down on the right, and I'm drawing it deliberately uneven. Look, side A, B is clearly shorter than side A, C. This is the triangle that should destroy the whole argument, and I picked it on purpose. If I can convince you this thing is isosceles, I've convinced you every triangle is. Now we're going to build two special lines inside it, just two. The first one comes from the top corner, A. The second one comes from the bottom edge, BC. And where those two lines cross, we'll get a single point, and that point is going to be the engine of the whole proof. Everything hangs off of it. So watch how each line gets defined, because the definitions are the only thing we're allowed to use later. No cheating, no measuring, no eyeballing. Just the two rules that build these lines, and then pure logic on top. That's the promise of a proof, right? You give me the rules, I give you something you can't argue with. Let's do the first line. First line, from corner A I draw the angle bisector. That just means the line that splits the angle at A into two equal halves. If the angle at A is, say, 40 degrees, this line cuts it into 20 and 20. Perfectly fair, straight down the middle. I'll paint both little half angles the same color so you can see they match. That's the entire definition. This line makes two equal angles at A, and that's the only thing I'm going to squeeze out of it. Notice I'm not saying where it lands on the bottom. I'm not claiming it hits the midpoint of anything. I'm not claiming it's perpendicular to anything. None of that. All I've got is two equal angles at the top. That's a completely honest standard construction. Every triangle has an angle bisector from every corner. Nothing weird here. Keep that yellow line in your head, the one splitting A in half, because in a minute is going to team up with the second line. And the second line is where people usually assume the trick is hiding. It isn't, but let's build it anyway and see. Second line, this one's about the bottom edge, BC. I find the exact midpoint of BC, the point that's the same distance from B as it is from C. Then from that midpoint, I draw a line straight up, perpendicular to BC, 90 degrees, dead vertical relative to that edge. This is called the perpendicular bisector, and it has one beautiful property I want you to lock in. Every single point on this line is equally far from B and from C. That's what perpendicular bisector means. Stand anywhere on it, and B and C are exactly the same distance away. That fact is going to matter a lot later, so I'm putting it on screen. Any point on this line has PB equals PC. Now here's the key move. I've got two lines, the yellow angle bisector coming down from A, and this perpendicular bisector coming up from the middle of BC. Two lines in a plane. Unless they're parallel, they cross somewhere, so let them cross. Call that crossing point P, and now watch, because P inherits properties from both lines at once, and that double life is exactly what makes the proof so convincing. There it is, point P, where the two lines meet, and P is special because it's on both lines, so it obeys both rules at the same time. Rule 1, because P is on the angle bisector from A, the line AP splits the angle at A into two equal pieces. Rule 2, because P is on the perpendicular bisector of BC, we know PB equals PC. P is exactly as far from B as it is from C. Hold both of those. Now I'm going to do one more thing to P. From P, I drop two little perpendicular lines, one over to side AB, hitting it at a right angle at a point I'll call E, and one over to side AC, hitting it at a right angle at a point I'll call F. So E is the foot of the perpendicular on the left side, F is the foot on the right side. Two clean right angles marked with little squares. That's the full setup. A, B, C, the two lines, the point P, and the 2 feet E and F. Everything from here is just comparing triangles, and the triangles are going to match up suspiciously well. Look at two little triangles up near A, triangle APE on the left, and triangle APF on the right. I'm going to argue they're identical, same shape, same size, just mirrored. Watch the pieces. First, the angle at A. We split it in half with the bisector, so the angle inside the left triangle equals the angle inside the right triangle. Match number 1. Second, the right angles. E and F were both built as perpendicular feet, so both triangles have a 90-degree corner. Match number 2. Third, they share the side AP. It's literally the same segment, the border between them. Match number 3. So I've got two triangles agreeing on an angle, and the side between the story. That's a legitimate congruence rule. Angle, angle, side. These two triangles are congruent. Full stop. And when triangles are congruent, all their matching parts are equal. So I get two facts for free. AE equals AF, the top pieces of the two sides match. And PE equals PF, the two little drop segments match. Both true, both airtight. I'm circling them. We'll need them both. On to the next pair. Now the bottom pair. Look at triangle PEB on the left and triangle PFC on the right. Same game. First, both have a right angle at E and at F because those were perpendicular feet. Match 1. Second, remember PE equals PF. We just proved that from the top triangles. Match 2. Third, remember PB equals PC. That came from P living on the perpendicular bisector. Match 3. So now I've got two right triangles with a matching leg and a matching hypotenuse. That's a valid congruence too, the right angle hypotenuse leg rule. So triangle PEB is congruent to triangle PFC. And again, matching parts are equal, which hands me the fact I actually want. EB equals FC. The little leftover piece on the left side equals the little leftover piece on the right side. Let that land. From the top congruence, the upper chunks are equal. AE equals AF. From this bottom congruence, the lower chunks are equal. EB equals FC. Two equalities, both earned honestly through standard congruent triangles. Now I just add them together and the whole thing snaps shut. Here's the finish. Side AB is made of two pieces, the top piece AE plus the bottom piece EB. That's just the whole side split at point E. Same story on the right. Side AC is the top piece AF plus the bottom piece FC, split at point F. Now substitute. We proved AE equals AF. We proved EB equals FC. So AB, which is AE plus EB, has to equal AC, which is AF plus FC. Equal plus equal is equal. Therefore, AB equals AC. The two sides are the same length. This triangle, the deliberately lopsided one I drew specifically so this couldn't happen, is isosceles, and I never used anything special about it. Any triangle you hand me, I run the exact same construction and get the exact same conclusion. So every triangle is isosceles. There's the proof. It feels bulletproof. Every congruence was a real rule you'd get full marks for on a test, and yet the conclusion is garbage. So somewhere in that chain, one step told you a lie with a straight face. Let's go find it. Let's be detectives about this. Which steps could actually be wrong? Walk back through. The angle bisector splitting A in half. That's just true. It's the definition. The perpendicular bisector giving PB equals PC. Also just true by definition. The first congruence, angle, angle, side. The pieces genuinely match. That rule is real. The second congruence, hypotenuse leg, the pieces genuinely match. That rule is real too. The final addition, whole equals part plus part, that's about as basic as arithmetic gets. Every individual claim checks out when you test it in isolation. That's what makes this thing so nasty. Nobody's step is false. So how do you get a false conclusion out of all true steps? Here's the tell, and it's a big one. Every single thing we did by reading it off the picture. Where's P? Down inside the triangle. The picture says, where's E? On side. AB, the picture says. Where's F? On side AC, the picture says. But nobody proved any of that. We drew a convenient triangle and trusted the drawing. The lie isn't in a step. The lie is in the diagram. Let me draw it honestly and show you what's really going on. Watch what happens when I stop faking the picture and build P accurately for our lopsided triangle. I'll actually construct the angle bisector, actually construct the perpendicular bisector, and let them cross wherever they really cross. And there, P is not inside the triangle. It's outside, dangling below the edge BC. That already feels wrong compared to the cozy little diagram from before, right? But it gets better. There's a genuinely lovely reason P sits there, and it's worth a second. The angle bisector from A and the perpendicular bisector of BC both pass through one famous point, the spot on the triangle's circumscribed circle right at the middle of arc BC. So they're guaranteed to meet, but for an uneven triangle they meet way out on that circle, well outside the triangle itself. That's not a coincidence, it's forced. The more lopsided the triangle, the further out P drifts. For an actual isosceles triangle, the two lines would collapse into each other and P would sit nicely on the base. But for everyone else, P escapes. And once P is outside, the two little feet E and F stop behaving the way the fake picture promised. Here's the actual punchline, and it's so small you'd never suspect it. When I drop the perpendicular from P to each side and mark where the feet really land, watch closely. One foot lands on the side, right where it's supposed to, between the corners, but the other foot lands outside the side, past the corner, on the extension of the line, not on the triangle's edge at all. One is in, one is out, every time, for a lopsided triangle. Now go back to the killer step. I said AB is AE plus EB, and AC is AF plus FC. Whole equals top piece plus bottom piece. That's only true if the foot is actually sitting on the side. For the side where the foot landed outside, the real relationship isn't plus, it's minus. The side is the difference of the pieces, not the sum. So one equation should read AE plus EB, and the other should read AF minus FC. Feed that in, and the two sides do not come out equal anymore. The congruences were all true. AE really does equal AF. EB really does equal FC. But you cannot add them the same way on both sides, because one foot ran off the edge. So the entire illusion rides on one unstated assumption, that both feet land on the sides. So both sides split the same friendly way. We never checked it. We just drew a picture where it looked true and marched forward. And that's the whole lesson, honestly. A proof that leans on a diagram is only as trustworthy as the diagram, and diagrams are really good liars. They quietly decide which points are inside and which are outside, which side of a line you're on, and if you never question that, the picture can smuggle a false assumption into a chain of perfectly true statements. This is exactly why the way mathematicians write proofs got so fussy and, honestly, so ugly to read. All that pedantic case checking. This point lies between those two. This foot is on this segment. It feels like joyless bookkeeping, but this is what it's protecting you from. One innocent, unchecked in or out fact, and you've proven every triangle is isosceles. The picture felt like help. The picture was a trap. The math never lied to you. You lied to yourself with a convenient sketch, and the math just went along with it. So we caught it. The broken move wasn't a broken rule. It was a foot quietly stepping off the edge while we weren't looking, and a plus sign that should have been a minus. Here's the thing that still bugs me though, and I'll leave it with you. This same trick, hiding a false assumption inside an innocent looking diagram, has fooled genuinely brilliant people for centuries, not just in cute puzzles. Whole arguments in the history of geometry quietly assumed a point was inside when it was outside, or that two things crossed when they didn't, and nobody caught it for ages. Which makes me wonder about the proofs we trust right now. How many of them are leaning on a picture in our heads that we've just never bothered to check because it looks so obviously fine? Probably some. We won't know which until someone draws the honest diagram. Anyway, next time somebody shows you a proof and every step looks perfect, don't ask whether the steps are true. Ask what the picture is quietly assuming. That's where the bodies are buried. Go draw a really lopsided triangle and watch that point run off the edge. It's weirdly satisfying.